Hi guys, this is an undergraduate course on group theory, and today we will discuss subgroups. Well, we already have gone through these concepts like binary operations, their properties, groups. We have seen a variety of examples. Then we also learned how to compute order of an element in a group, and we also proved some basic properties of groups. Here are the contents we will discuss today. We will define subgroup, we will see some basic examples, and there are some nice tests to prove a subgroup. Then there are some nice examples and exercises. Subgroups, by definition, a subset H of a group G is called a subgroup of G if H itself is a group under the operation of J. We use this notation H less or equal to G to mean that H is a subgroup of J. If H is different from J, then we simply write H is subset of J. Such a subgroup is called proper subgroup. This subgroup consisting of only identity element is called trivial subgroup, and subgroup that is different from this A is called non-trivial subgroup. Here are some elementary examples. Set of integers. We already have proved that set of integers is a group under addition because it's a subset of R. So that's why by above definition we can say it is a subgroup of R. The same applies to set of rational numbers and set of real numbers as well. So note that when we talk about multiplication of real numbers, it's understood that we are taking the zero element to be not to be in R. So we take that zero out when talking about multiplication. So under addition modulo 6, this subset 0 to 4, it is a subgroup of Z6. It's quite simple. If we take set H of all these matrices with real entries, it becomes a subgroup. So we actually have proved that it becomes a group. Now it's a subset, so we can call by above definition it is a subgroup. So you see, so far if we want to prove a subgroup, then we have to go through the axioms of group, because definition is actually, by definition, a subset becomes a subgroup if really that itself is a group. But here next we have actually some tests. So the question is how to prove a subgroup. So that is, when determining whether or not a subset H of a group G is a subgroup of J, we need not directly verify the group axioms, as we have the next three basic interesting tests. The first one is one-step subgroup test. We will abbreviate by ST1. So this theorem ST1 says let G be a group, H a non-empty subset of J. If AB inverse belongs to H, whenever A and B are in H, then H is a subgroup. So when it's addition, of course this AB inverse notation is denoted by A minus B. So the proof follows from the definition. So we will prove the four axioms of group. Since it's a subset, so every subset of a group satisfies the associative law, because it's a subset, so there is no problem with associativity, it's quite clear. So the next thing we show that is the neutral element, the identity element exists in H. So look here, because AB inverse belongs to H for every pair of elements. So in particular, if we take AX, B again X, then consequently X inverse is nothing but E. So it means E belongs to H. Okay. So the existence of inverse. For example, if we choose this A to be E, because now E exists in H, and B say some X, then definitely E X inverse belongs to H. E X inverse means X inverse belongs to H. So inverse of every element is there, and finally we prove the closure that H is closed under this operation. So we take X and Y from H, because we have proved that for each Y inverse is also in H. So that's why we let A to be X and B to be Y inverse, and inverse is nothing but the element itself, and this is nothing but AB inverse. So it means H is closed under the operation. So by above definition, it satisfies all the axioms of group, hence it becomes a group, and because it was a subset, now we can call it is a subgroup. So it is a two-step subgroup test. So here are two things. The one is about closure, the other is about inverse. If AB belongs to H whenever AB comes from H, and A inverse belongs to H whenever A belongs to H, that is H is closed under the operation, H is closed under taking inverses, then we say it becomes a subgroup. So the proof is quite simple. We use above theorem and we just show that AB inverse belongs to H. So now if you want to use ST1, we simply have to prove that AB inverse belongs to H. So we take two elements A and B. Since it is closed under taking inverses, so B inverse is there, and because H is closed under the operation, so AB inverse belongs to, and then we are done. So above theorem we can say now it is a subgroup. Okay, so these two tests, ST1 and ST2, can be applied to any subset of a group. Doesn't matter it's finite or infinite. But for finite case we have another test, namely finite subgroup test, and it's more simple. We have a non-empty finite subset of a group J. If H is closed under the operation of J, then H is subgroup of J. So we will use above theorem to prove this, and because it's already closed, it means by two-step subgroup test ST2 we will need to show that A inverse belongs to H whenever A comes from H. So there are two cases. If A is identity element, then we are done, because in that case inverse of A is nothing but A itself. If we assume that A is different from A, okay, then we consider all the powers of A, then A squared, then A cubed, and so on, since H is closed. So it means all these powers belongs to H, but H is finite. It means not all these elements are distinct. Some powers coincide. For example, say AI is equal to AJ, assuming that I is bigger than J. Simply we can write A I minus J is A, Note that because A was different from A, it means I minus J definitely is bigger than, here it's bigger than 1. Okay, this simply can be written as this, since now it becomes power of A, so that's why it belongs to H, and we are done. Quite interesting, very simple. So it means if a given subset is a finite subset, then we can use this test to prove that that finite subset is a subgroup. An important thing to note, so how do we prove that a subset of a group is not a subgroup? Okay, so there are three possible ways. So any one of which guarantees that the subset is not a subgroup. In case there is no neutral element in that set, then we say it's not a subgroup. If there is some element whose inverse is not there, whose inverse is absent in that set, then we say it cannot be a subgroup. And if we take two elements and if the product is not there, then we say it cannot be a subgroup. Okay, here we have some nice examples. Multiple of z, so set of integers, so we multiply some integer, then it becomes a subset of this z, and under addition it becomes a subgroup. So we can use st1, st2 because it's an infinite subset, so that's why st1 and st2 both can be applied, but finite subgroup test cannot be applied here. Similarly, there's an infinite set, it's a subset of R, so st1 can be applied here to show that it becomes a subgroup. Here 2x plus y is 0. It's a set of all ordered pairs which satisfy 2x plus y is 0. That is, it's a straight line passing through origin, and it becomes a subgroup of R2, that is xy plane, and the operation is coordinate wise addition. Quite interesting. Okay, and I believe you are familiar with these notations, M to Z. So it's a set of all 2 by 2 matrices with entries from integers, and it becomes a subgroup of M to R. And with respect to addition modulo 10, 0, 2, 4, 6, 8 is a subgroup of Z10. Okay, set of all symmetric or skew symmetric matrices, it becomes a subgroup of M and R. So we can use st1 or st2 here. So set of all matrices of this form, it becomes a subgroup of GL2R. So note here 0, 3, 5, it's not a subgroup because it's not closed. And we take a group, there is an arbitrary element from A, so we take this set of all powers of A, all powers, positive powers, negative powers, integers, positive integers, negative integers, and 0 as well. So this is denoted by this notation, angle bracket open and closed A. So it becomes a subgroup. Let's see how. Because this A belongs to itself, if we take n is equal to 1, then it's not empty. And if we take 2 powers and apply st1, that is first element inverse of second, then this becomes simply a k minus l, and it is actually a power of A, and it belongs to that set, so we can say it's a subgroup. And other important thing, the intersection of two subgroups is a subgroup, and but the union, no, union cannot be, may or may not be. So I leave as an exercise for you to give an example that this union, the union of two subgroups may not be a subgroup. Here are some exercises for you. These are quite interesting and I advise you to try these exercises. So one is about matrices, second, so this third exercise, so it's let it be a subgroup of R under addition. So look here, so this was almost an example above there here. So I believe you see the similarity between this example and this exercise. And this exercise 4 is about functions. So we have seen the group of functions, so you just need to check that it's a subgroup. Okay, this exercise 5, it's again about 0 to R matrix multiplication works here. So guys, these were subgroups. So I hope you enjoyed, and in the next lecture we will discuss some cosets and Lagrange's theorem. Thank you very much.